Chapter 4: Quantum Field Theoretical Analogies and the Vacuum Structure of Numeric Space. The mathematical framework that redefines zero as a supersymmetric origin state achieves its deepest physical validation when viewed through the lens of quantum field theory, especially in the analysis of the vacuum state. These analogies are not superficial metaphors, but are rooted in genuine mathematical and physical correspondences that illuminate both the emergence of number from the zero state and the observable phenomena of quantum vacua. In effect, the vacuum of quantum field theory stands as the closest physical analog to our mathematical zero state, mirroring its key features of maximal symmetry, suppressed expectation values, and latent generative potential through symmetry breaking. In quantum field theory, the so-called vacuum state, denoted as ket0, is rigorously defined as the state of minimum possible energy, the reference configuration against which all physical excitations are measured. Despite its reputation as empty space, the quantum vacuum is anything but void. It is replete with incessant virtual particle-antiparticle fluctuations, persistent zero-point oscillations, and intricate patterns of quantum correlation, all of which manifest as measurable physical phenomena under the right conditions. A key property of the vacuum state is that, for any local field operator, let us call it phi hat of x, the vacuum expectation value is strictly zero due to the underlying symmetries. In spoken mathematics, the inner product of the vacuum state with phi hat of x acting on the vacuum state equals zero. This reflects the perfect balance enforced by symmetry. All positive and negative contributions in the vacuum cancel, just as in our supersymmetric zero state, the expectation value of any operator that lacks full symmetry vanishes when averaged over the zero state. Both systems exhibit suppressed first moments, signifying that their symmetric configurations mask any net value, even as they encode deep internal complexity. However, neither the quantum vacuum nor the supersymmetric zero state is truly inert. Both support non-trivial fluctuations that are captured by higher-order moments. For instance, the vacuum expectation value of the square of a field operator, which is the expectation value of phi hat squared of x in the vacuum state, is not zero. This non-vanishing variance reflects the persistent fluctuations of the vacuum, just as the numeric zero state exhibits measurable variance in the outcomes of numeric measurements, even as its average remains precisely balanced at zero. Among the most direct experimental validations of quantum vacuum structure is the Casimir effect. In this phenomenon, placing two conducting plates in close proximity alters the spectrum of permissible vacuum fluctuations between them, leading to a measurable force. This so-called Casimir force is a direct manifestation of quantum zero-point energy and is entirely attributable to modifications of the vacuum structure imposed by the boundary conditions. The force per unit area between two perfectly parallel plates separated by a distance a is given by the formula minus pi squared times h bar times c divided by 240 times a to the fourth power. This attractive force arises from the difference in vacuum energy densities. Between the plates, only discrete electromagnetic modes are allowed, while outside the plates, the field remains unconstrained. Mathematically, the Casimir energy is computed by summing the zero-point energies of all allowed discrete modes and then subtracting the contribution from free, unconstrained space. Explicitly, the regularized vacuum energy equals 1/2 h bar times the sum over discrete mode frequencies omega sub n minus 1/2 h bar times the integral over omega of omega times the density of states in free space. This regularization procedure is essential. Without subtracting the infinite free space contribution, the result would diverge. This is precisely analogous to our regularization of the infinite superposition defining the supersymmetric zero state, in which divergent sums are rendered finite by systematically removing redundant or non-physical contributions while preserving all physical meaning. The physical message is clear. The so-called empty vacuum is endowed with sufficient internal structure to generate observable effects, and these effects arise directly from the properties of symmetry and superposition, regularized to avoid infinities. In both quantum field theory and in our numeric framework, it is the boundary conditions, the constraints or measurements imposed, that break the initial symmetry, causing latent fluctuations to become manifest as real, measurable effects. A further crucial parallel is provided by the phenomenon of spontaneous symmetry breaking. In many quantum field theories, the fundamental Lagrangian, the function governing the dynamics, is fully symmetric, but the vacuum state is not. For example, consider the Mexican hat potential, expressed mathematically as minus mu squared times phi squared plus lambda times phi to the fourth power. This potential has perfect symmetry about the origin, yet the vacuum state selects a specific non-zero value for the field, usually plus or minus mu, divided by the square root of lambda, thereby breaking the underlying symmetry. Observable phenomena, such as massless Goldstone bosons or massive Higgs particles, emerge from this symmetry breaking. This mechanism maps directly onto the process of numeric differentiation from the supersymmetric zero state. The initial state is a perfectly symmetric superposition of all numeric possibilities. A measurement, analogous to choosing a vacuum configuration, selects a definite numeric value, breaking the symmetry. However, the mathematical framework and the full superposition remain intact beneath the selection. The process does not destroy the symmetry, but merely hides it at the level of observed outcomes. The residual uncertainty, represented in physics by Goldstone modes, corresponds, in our numeric framework, to the quantum mechanical uncertainty that remains even after a specific number is observed. The path integral formulation of quantum field theory sharpens the analogy further. In this approach, the amplitude for the vacuum state to persist in the presence of external sources is computed as a sum, or more precisely an integral, over all possible field configurations. Each configuration is weighted by the exponential of the action, integrated over four-dimensional spacetime. In spoken mathematics, this means the vacuum-to-vacuum amplitude equals the integral over all field histories phi of the exponential of I times the spacetime integral of the Lagrangian plus j of x times phi of x, where j is an external source. This sum over all possible field histories is mathematically equivalent to our construction of the zero state as a superposition over all possible numeric values, each with its own symmetry-determined weighting. The generating functional, often denoted w of j, is defined as minus I times the natural logarithm of the vacuum-to-vacuum amplitude in the presence of the source j. This functional encodes all possible physical processes that can emerge from the vacuum state. Functional derivatives of w with respect to the source generate the hierarchy of correlation functions, which describe the statistical properties of vacuum fluctuations, directly analogous to how the moments of the numeric distribution in the supersymmetric zero state describe the statistical properties of numeric emergence. In summary, the analogy between our supersymmetric zero state and the quantum vacuum is far more than illustrative. Both structures represent the ultimate origin states, maximally symmetric, information-rich, and generatively potent. Both manifest observable effects only when their symmetry is broken, whether by boundary conditions, measurements, or other symmetry-breaking events. Both require regularization to translate infinite possibility into finite, meaningful outcomes. And both provide the deep foundation for emergence, not just of numbers or particles, but of all observable structure in mathematics and physics. By framing numeric emergence in terms of quantum field theoretical principles, we reveal not only a common mathematical skeleton, but a unified vision of how structure, measurement, and observable reality arise from the underlying logic of symmetry and its breaking. This is the ultimate architecture of vacuum and origin, rendered in both number and field.